Nice. So let's go through the wrong answers. It is possible to determine, so this is not correct. If you look only at the dominant eigenvector of A, you cannot say dominant eigenvector is more like a page rank, So it's or the eigenvector centrality is more. So it might give you a centrality measure, but not necessarily the good interpretation of how many discrete components there are. If you look at the second smallest eigenvector of L, you could extract something. You could extract the bisection, but it will not be very clear whether there are only there is a two well-connected disconnected clusters or completely disconnected. But if you look at the eigenvalues of L, and if you see that the first is 0, second is 0, that means at least one island, maybe there are more. So how many zeros you find, that many islands you will see in the graph. So by looking at the eigenvalues of L, you can determine how many disconnected islands there exist in the graph. Chicken, yes, it's a big lead. Last question. To cluster a graph based on conductance, one needs to examine the eigenvectors associated to Right, very good. So still majority guessed right. And you remember this was what we discussed. If you want a specific goodness clustering, specific goodness measure, you might need to look at the different types of matrices. So conductance was actually, you could solve it on looking at the eigenvectors, like looking at this low dimensional space where you extract with eigenvectors of normalized Laplacian. If you look at the of the matrix A, dominant eigenvalues you should not even take to start with, because you have to. So eigenvectors associated to eigenvalues. Yeah, that's. So if you look at the eigenvectors associated to largest eigenvalues of A, you will solve of the average degree. If you look at the smallest eigenvalues of L, or the vectors associated to smallest eigenvalues of L, you will solve of the ratio cut. This you solve on the conductance, and here, and if you look at the largest eigenvalues of L, that's completely bad, because you should look at the lowest for L. So that's a tricky one. This would be correct for solving for different clustering, and this will be completely incorrect because you should not look you look in the wrong direction basically. Okay, so the winner is chicken, not very surprisingly, because it was leading all the time. So who is the chicken? Great, so congratulations. Then this was the last Kahoot this year. But we have a few more slides to finish before we go for lunch. Yes. So the last point is graph representation learning, which is a little bit now what we discussed, how we represent a node in a graph in some low-dimensional space. And one way would be what we did here. Just a low-rank approximation. We map it into the coordinates of a dominant eigenvectors. But we can look at this problem from a bit different or ML perspective, and that's what people did in the recent years, and they find it very sort of surprisingly effective for real-world empirical data set. So basically, again, what we want to do, we want to map each node into low-dimensional space that later we can do something useful. Let's say a dot product would give us some good similarity that we later would do for link prediction or for clustering or for anomaly detection and so on. So basically, we take a graph. We can, of course, extract some of our regular matrix like A, And then we want to go in some low-dimensional matrix, low-dimensional space, where this matrix would give us the new coordinate that is very useful for, say, these things. And now what is useful is now the tricky part. So, but this is what we want to achieve. And the idea is the following. So there is this embedding space, there is this network, and we believe we understand similarity between two nodes. And of course the most naive similarity is just 0, 1, that there exists link or not. And that's what you get with this type of embedding, because you started with a 0, 1. Or you can have more involved similarity, let's say some kind of a random walks, the hitting time and so on. So you can have more sophisticated similarity measure, but you want that based on that measure, we somehow magically could encode this U and V into this embedding space such that this similarity will be proportional to the dot product between these two vectors in that space. And dot product is, in a sense, you can think it as a cosine similarity if the vectors are of the same length. Because cosine similarity is dot product over the product of the lengths, right? So we want to achieve that based on some kind of similarity measure. So yeah, you go, the idea is to get this table like this. Just now in this case will not be eigenvectors, because people believe this is not strong enough, because you just captured the 0, 1s here, you want something stronger. So how to do it? And actually, so there was probably one of the first that produced the papers, is called Deep Walk by Perozzi. And they, for example, the example was this karate graph here, that they, with this deep walk method, they ended up with this low dimensional space, and this is this two-dimensional space, where you could see that the coordinates that that now the colors represent the same node. So these guys that are very in the periphery of this network got peripheral IDs in this two-dimensional space. These guys also got somewhere far away. Those guys here are together. The blue ones also together. So somehow this represents the real world in this low-dimensional space. And maybe here you can do something useful. Say if there is a small distance between these 2 points, you can predict a link here, for example. And you would not predict a link between this and this guy because they're too far away, and maybe it will not happen in practice either. So you now want to do this smart way of transforming to low-dimensional space, but something more smart than what only eigen decomposition can give us. So basically, the plan of action is the following. We define an encoder, and this encoder is just nothing else as a table, like a lookup table that we have here. And we can start, say, with a random one. And then we want to, then you define a node similarity function, and that would be your probably domain specific. So maybe you will think of some kind of a random walk-based approach, or based on what something maybe spreads in your network, or this could be really domain specific. And then you want to, based on that similarity function that you defined, you want to massage this table or this encoder in such a way that the dot product of any two nodes would give high similarity if it's high similarity in what you defined. Okay, and this massaging would be basically some gradient descent in our ML technique. So okay, so we take this network, we define similarity. We can use similarity says from the beginning of the class or something maybe more involved. And usually in the latest literature, it's mostly this random walk approach, some kind of random walk strategy that defines the similarity between two nodes. So somebody says, now my similarity would be if I go with that random walk strategy, like with this probability in that direction and less probability in that direction, because it somehow reflects my problem I'm solving. And based on that similarity, I'm going now to massage this table that gives us the mappings of the nodes into the low dimensional space. And there I will, once I have this correct mapping, I can do many cool stuff. So what they do is the following. They define the strategy, and the most simple strategy is actually just a random walk. The most simple strategy. And they do it in such a way that basically that the probability that say that you will reach a node v from node u would be proportional to the angle of the vectors in this low-dimensional space. Okay, so and the angle is basically cosine similarity or some kind of a function of a dot product. And I will not go deeper, so every paper has some kind of a fancy stuff of optimizing it, but it's basically you can think of it as a dot product. Okay, so the idea is the following: you define a strategy, you walk, you collect your walks, and then based on what you see in the walks, you try to make sure that whatever you saw in a specific walk, dot products of these nodes that you saw in the same sort of chain would be optimized, you know, being as high as possible. And you do it with some ML box, usually stochastic gradient descent. And that's where these many quite famous works now very well cited, like Deepwater, Node2Vec come into play. So okay, so we take a network, you do some kind of random walks based on some strategy, you collect these random walks, and now looking at these random walks, you basically push it to your stochastic gradient descent, to your ML box, and try to massage this embedding matrix so that say the dot product function, it's usually in some cases like a sum of the log over the exponents of a dot product would be maximized based on if they were observed in the same random walk. So there are many iterations of that, but this is nothing else as trying to define yet another empirical way of measuring similarity. So this is not as precise as we did before, where we say similarities, you know, cut centrality, and that's it. Here is just say, I am walking, you know, and I'm walking, you know, 1,000 times from this guy, and then I collected this observation. I then optimized the coordinates of these nodes that I observed such a way that they are maximal, gives this maximal dot products or the sum of the logs of dot products in the final score. And so there are this many of these approaches, and you use it for many interesting sort of domains like anomaly detection, attribute prediction, clustering, link prediction, and so on. And they claim they work better than a simple, say, eigen decomposition, where you simply map the coordinates into the eigenspace and take the dominant eigenvectors, because you can capture a bit more sort of fine-tuned phenomena than simple, you know, sort of here would be just the internal, sort of the clustering of an internal degree or something. And another cool thing is that sometimes you don't even need to know all the underlying network. Because here, in order to produce these vectors, we have to know the underlying network. Sometimes we just know the cascades. So for example, if you observe how Twitter this retweets happened, it's like a cascade. This tweet was retweeted by this guy, this guy, this guy. Other tweet was retweeted this guy, this guy, this guy, this guy, and so on. So you collect the cascades of tweets, and you maybe not even know the actual underlying social graph of Twitter. While still you could infer a good representation of every node in this low-dimensional space for Twitter users. So this could be even network agnostic. So there are many of these strategies. So the first, I think, and the most famous is deep walk, is basically non-biased random walk. And then there were different kind of biased walks. And I think out of those the most prominent is Node2Vec. And Node2Vec is basically doing a trade-off between random walking in the breadth-first search fashion and depth-first search fashion. So you have some hyperparameters that can let you go either more breadth-first search way, just looking, you know, collecting the neighbors around your immediate community, or going deeper and deeper, sort of collecting observing the network more in depth. And there are many other ways to do it. I was involved in some of them with my visiting students on a network agnostic strategies, where exactly we inferred the the user representation low dimensional space on the how they were tweeting on Twitter. So basically we were doing this completely in a network agnostic fashion, where we don't even need to know how the network is produced, but we just observed what happened on top of the network, and from that by this network representation learning, we map, we massage this table such that it has pretty good coordinates that can solve some of our predicting tasks. And what I want to remember that this is quite powerful, because you can now choose your strategy how you collect these neighbors based on your domain-specific problem. So this is a bit more flexible than what we saw before, where we only looked mostly in the topology-based way, while here you can say I will random walk that direction as long as maybe there is some kind of content base, like if you observe some, I don't know, the collaboration networks, whether if you have the same domain and publishing, you walk that direction. If not, you go backwards, and you can define many interesting strategies that reflect your problem, and then you'll have more useful mapping into slow dimensional spaces. And actually that is that. So I want to thank you for bearing with me, and again I overflow for 5 minutes, but that is the last time, so I will not bug you anymore. I see you next Monday, when I will listen to some of your presentations together with our TAs, and then Wednesday there is no lecture. I will write it also on Canvas, but you don't need to come. I think it's scheduled, but there will be no, and only the lecture will be on Friday with invited speaker. So, do you have any questions on? Otherwise, thanks again, and then have a good weekend. Thank you.
Just one small question.
Yes, sure. I just turn off the camera then.